our degrees of freedom of 3. So degrees of freedom of 3 and a tail probability of 0.05 puts us at 7.81. So 7.81 is our critical value. All right, so what does that mean? Well, we have to know what we're actually testing. So let's go back and write our hypotheses. So the problem is looking at whether the blood types in the community match the blood types in the population. So our null hypothesis, which again means nothing is different, nothing has changed, would say the community's blood type. So the null hypothesis would say the community's blood type distribution is the same as the general population's distribution of blood type, right? So it's the same. So then our alternative hypothesis says the community's blood type distribution differs from the general population's distribution. So this is one of those cases where, yes, it's one-tailed because it is a chi-squared test, but if we were thinking in terms of normal distribution, it would almost be two-tailed. It's a not equal to. But we don't know which way it's not equal to. That's not going to tell us that. The only thing chi-square is going to tell us is yes, it's the same, or no, it's not. And so when we look at those hypotheses, it really doesn't help us in terms of the model, but it does say that yes, it is the same, or no, it differs from it. Okay, so going back to our actual data and what we have here for our test, we have a chi-square value of 3.2465 and a critical value of 7.81. So with our chi-square test statistic being 3.2465 and our critical value at 7, then we know that with chi-square equaling 3.2, we're just going to say 5, and that being less than our critical value of 7.81, we're going to fail to reject because it's not as varied or as extreme as we need it to be in order to reject that hypothesis. So we're saying that it is probably similar. So with our chi-squared being less than our critical value, I fail to reject the null. Now with our other tests, one of the things we've used is our p-value. And you can use a p-value for the chi-square test statistic, and that's not a problem, but in order to get that p-value, you have to use technology. You have to use Excel or you have to use a graphing calculator. So you can watch the other videos on that if you would like to. If you just want to know the p-value for this test, this example was 0.355. So 0.355 is a fairly large p-value. And so we are going to continue to fail to reject because that's so large. Okay, the next test is the chi-square test of independence. That means that we are seeing if one of the categorical variables is independent of the other. So you're looking at two totally different categorical variables and seeing if one has an impact on the other or if they're totally independent. Okay, so when you deal with the test of independence, your chi-square value is found the same way. It uses the same calculations, everything's the same. It's simply that your hypotheses are different, and so your chi-square value is giving you a different meaning in terms of the test and your data. So again, same chi-square, same degrees of freedom, but what it's going to do is it's going to classify data from a single group on two categorical variables, which we already discussed. And so your null hypothesis will talk about those two categorical variables. This variable and this variable are independent, or there is an association between this variable and this variable. Not necessarily that one is dependent, just that there is an association. Similar to the one before, you don't know that it's higher or lower, you just know that it's not the same. All right, so let's go ahead and do an example. We're talking about Mr. Kai's students. And what we want to know is whether hand dominance is independent of eye color. We're using a 0.05 significance level for this. So let's go ahead and write our hypotheses first this time. Going off of our notes and our example in our notes, it says your blank and blank are independent. So the two things we're looking at are eye color and hand dominance. So our null hypothesis is going to say eye color and hand dominance are independent. So then our alternative hypothesis is going to say there is an association between eye color and hand dominance, because that is what we're looking at. Going to our data, the first thing we need to do is find our expected values. So we need to use that formula that we were given before to find expected values, where it's row total times column total divided by total total. Okay, so let's go ahead and find our totals before we start our expected values. So the total of left-handeds would be 19. The total of right-handeds is 95. Then you need to find your row totals. The total of brown would be 42. The total of blue is 33. The total of green is 23. And the total of other is 16, which gives us a total of 114. Okay, now that we have our chart built, we need to go ahead and find our expected values. Row total times column total divided by total total will give us the following values. Okay, once you find all of your expected values, you'll notice that this goes against one of our conditions. If you look at the green and the other, for left-handed people, it doesn't give us an expected value of at least 5. And without that expected value of 5, you can't run your goodness of fit test. So remember, one of the options was to scrap the whole thing or combine things together. And since green and other are both so small, we can put those together into one other category. So green would just fall into the other category. So let's go ahead and do that. So now we have to go back to our data, and when we put those together, that's going to change our row total. It's not going to change our column total, it's just going to change that row total. So when we put those together, our new row total is going to now be 39. So now when we find our expected values, we will need to use 39 as our row total, which will end up giving us our expected values of 6.5. So now we have our expected values that are all over 5 or more. Now we can run through our chi-square statistic. So that chi-square statistic is going to, you need to add all of the cells together. You need to do all of that work. You need to do the observed minus the expected, square it, divide by the expected, and add all of those up for every single cell. Okay, when you go through and do that, you will end up with a chi-square value of 0.708. Once we have that, we can find our degrees of freedom. Degrees of freedom is a little bit different here. Before it was just our cells minus 1. Now when you look at our notes, it's the number of rows minus 1 times the number of columns minus 1, not the number of cells, the rows and columns. So we have 3 rows, minus 1 would be 2, 2 columns, minus 1 would be 1, which puts us at 2 times 1, 2 times 1, rows minus 1 times columns minus 1 to give us a degree of freedom of 2. We are told our alpha level is 0.05. So let's go ahead and look at our chart. Degrees of freedom 2 at 0.05 for our alpha level. Degrees of freedom at 2 with 0.05 for our alpha level gives us 5.99 as our critical value. So when you look, our chi-square value is fairly small. It's not even 1, so it's not really all that different, okay? And so when we go ahead and look at this, we have a critical value of 5.99. So again, just like up above on our previous example, with chi-squared equaling 0.708, which is less than our critical value of 5.99, I fail to reject. Failing to reject the null in this case means that there is not sufficient evidence that shows an association between eye color and hand dominance. So when I ask you to tell me what that means in terms of the problem or given context, that's what you're going to say. There is not sufficient evidence to claim there is an association between eye color and hand dominance. Okay, so that's our chi-square tests. We have 2 of them, and those are the only 2 that we're going to look at right now. because everything else is pretty much the same. You're just going to follow the same pattern. You're going to find your chi-square, and then you're going to work through everything. When you look at a test of homogeneity, that means you are comparing to see how the two different samples compare, whether they're the same, whether they are homogeneous. And so you're running the same chi-square test as goodness of fit. It's going to look the same. You're going to run the same thing. You're going to find the same chi-square value, find your critical value, and it's going to proceed as normal. So if you run into that need for that test, then you're going to do it the exact same way. All right, hopefully that helped and cleared up a little bit of the chi-square stuff, and now we have a better understanding of it all. I look forward to helping you throughout this unit. Make sure you ask questions if you have them or as they arise, and good luck.